Good morning, Spicy Pepper. How are you? I am okay. I let's see. Yeah, I'm okay. A little bit tired this morning, but can't complain overall. Waiting for the number of viewers to go up. Um, going to be talking about electric flux today. All right, I think I've reached the critical number where I am going to begin. Good morning, everyone. Welcome to another edition of AP Physics C / IB Physics HL. So today we are going to talk about something called the electric flux. Okay, or flux of the electric field, something like that. And someone gave me a dislike. I can only see likes from my studio view. So the first thing, and it's we're gonna kind of build up to the actual definition of electric flux, but so we're gonna build up to it. But the first thing that I need to introduce to you is the idea of an area vector. Okay, so let's suppose you had a rectangle. Okay, and I'm trying to draw this as in a three-dimensional sense. Okay, and let's say it's an L by W rectangle. The area vector points perpendicular to the surface. Okay, and the length of the area vector is equal to the area of that surface. So this vector would have a length L times W. So the area vector would be LW, and since it points in the y direction, I would say LW times J hat. If you had a different shape, something like a circle, so maybe you have a circle that's oriented this way. The area vector is going to be perpendicular to the circle, so it would point in this direction. And then maybe the radius of that disk is r, and in this case, the area vector would be pi r squared, because that's the size of the area, and then it points in the I hat direction. Okay? So to summarize, the area vector points perpendicular to the surface and has length equal to the size of the area. So that is the area vector. Now keep in mind that really there are sort of two area vectors for any given surface, because this direction is also perpendicular, okay, to the circle, and this direction is also perpendicular to the rectangle there, okay? So if you have a surface, you kind of have two directions, or two options for your area vector. So maybe I should say plus or minus and plus or minus. But in most cases, there's a convention that will follow, and I'll talk about that in a second. So that is the area vector. The next thing I wanted to do is I wanted to do just a quick review of the dot product. Okay, so if you have two vectors, let's say v and w, there is some angle between them, which I will call theta. Then the dot product, which is denoted by v dot w, is equal to the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them, okay? And so in particular, if you have two vectors that are parallel, so what if v and w are parallel to each other? In that case, theta is equal to 0, and cosine of 0 is equal to 1. So in this case, v dot w would be equal to just magnitude of v times magnitude of w. If you have a situation where v and w are in opposite directions, so maybe v is going this way and w is going this way, then in this case the angle is 180 degrees, and the cosine of 180 degrees is -1. So v dot w would be magnitude of v times magnitude of w times -1. Okay, so it's negative v times w. And in the case of v and w being perpendicular to each other, this is going to be theta equals 90 degrees, and the cosine of 90 degrees is 0, and so therefore v dot w equals 0 in this case. Okay, so all three of those cases are going to be important for this lesson. Okay, so now we're ready to define the flux of the electric field. Okay, so the flux of the electric field is what you need in order to calculate it is you need a surface, okay, and you need an electric field that is defined on that surface. And so what the electric flux is, now oftentimes flux is represented by a capital Greek letter phi, so you put phi sub E. It is going to be equal to the value of the electric field on the surface dotted with the area vector of that surface. Okay? All right. So it's going to be magnitude of E times magnitude of area times cosine of theta. Okay, and keep in mind, this is where it becomes important when you are defining the flux of the electric field. The area vector points normal to the surface. Okay, so remember when I do magnitude, sometimes I just drop the arrow. So I can write it as EA cosine of theta, where there's no arrow above E or A, so I mean the magnitude of those quantities. The units of electric flux, well, it's an electric field times an area. So you have newtons per coulomb is the unit of electric field, and then square meters are the unit of area. So electric flux is measured in Newton meters squared per coulomb. Let's suppose you have a situation like this where here is your surface, okay, and then here is your electric field. The electric field is parallel to the surface, like that. All right. What is the electric flux in this case? Well, in this case, remember the area vector points normal to the surface. Okay. Points normal to the surface. And so in this case, the angle between the electric field and the area vector is 90 degrees. Okay. And if the angle is 90 degrees, then the dot product is 0. So this would be a flux of 0. So, ladies and gentlemen, this electric field gives 0 flux through this surface. Okay? But if we took the same electric field and we instead passed it through that circular surface, one that was like this, okay, this one had an area vector that was going in that direction, and so here the area vector, the angle between the area vector and the electric field is 0. Okay, so so in this case, the flux is going to be E times pi r squared. Okay, because the magnitude of the electric field is E, the magnitude of the area vector is pi r squared, and the angle is 0. All right. So we could actually imagine a more complicated surface that is built up out of subsurfaces. So for example, what if I had something like this, where it's like two sides of a cube, okay? And maybe the electric field is going pointing in this direction, like this. All right. So if I call this surface 1 and this surface 2, surface 1 has an area vector that points that way with that angle. Okay. So I should call that theta 1. And then surface 2 has an area vector that points that way. And so your angle is going to be that angle. And so if you have a surface that's made up out of multiple subsurfaces, then what you're going to have is the total flux through that surface is going to be E1 dot A1 plus E2 dot A2. All right, because there are two electric fields and there are two areas that make up the surface. Now, I'm going to give you another notation for electric flux. This is the more common notation, more common than that. And we write it as an integral of E dot dA. Okay. E dot dA, and then we could even put a little s here where we mean over a particular surface. So this is the flux of the electric field through a particular surface S, and all this means is E1 dot A1 plus E2 dot A2 plus dot dot dot, where we are summing over all of the different subsurfaces of the total surface. Okay, so and this is the definition of flux in general. So this is the flux of the electric field, but you could also have, flux of velocity, flux of the magnetic field. Okay, so anytime you have a whatever this vector is, it's the flux of that particular vector. Okay. All right. Sometimes the surface is what is called closed. So some examples of closed surfaces are like this. So this is a spherical closed surface. Okay. You could have another common one that we will encounter is a cylindrical closed surface. So a closed surface is one that is containing a volume of space, right? You could have a cubical closed surface. Okay. So if you are trying to find the flux of the electric field through a closed surface, okay, so again, closed surfaces are enclosing a volume of space, okay, completely. If we just take a sheet of paper is not a closed surface because it isn't, you can go around the sheet of paper to get to the other side, okay? A closed surface is one where in order to get from the inside to the outside, you have to pass through the surface. And you can calculate flux through closed surfaces. And the notation is just slightly different. So if it's an open surface, you write just integral of E dot dA. But if it's a closed surface, you put a little circle here. And circles are closed. They enclose a region of space, so that is why you put that on there. Okay? So it's just a little change in notation. All right? So how would we calculate the flux through here? And remember, this is just sum of E dot dA. Well, if we think about a cube has 6 faces, okay? So in this case, it would be just E1 dot A1 plus E2 dot A2 plus dot 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 all the way to E6 dot A6, where E1 is the electric field on the first face, E2 is the electric field on the second face, E3 is the electric field on the third face, and so on and so forth. Because the electric field doesn't have to point in the same direction on each face. You could have, for face 1 here, it points in this direction, and then for face 2, it points straight down, and then, I don't know, maybe for face 3 it points straight down, but maybe for face 4 it points this way. So you can have different electric fields on each of your faces that points in different directions, has a different size. Because this is a cube, the magnitude of each of those area vectors is going to be the same. It's going to be just a squared, where a is the side length of the cube. If you have something like a cylinder of radius r, and let's say it has a length L, you can have it, so you could think about it as 3 faces. You have a face on this end, you have a face on this end, and then you have a curved middle face, okay? Or I don't know what you want to call this central region, like the tube face of it, okay? And so if you wanted to calculate the flux through a cylinder, you would have, E electric field on the left end times pi r squared, because that would be the area of this left end, times cosine of theta on the left end. So maybe the electric field makes a certain angle with the left end's area, plus the right side, the flux through the right side. So maybe the electric field on the right side points in this direction, and so you would have the electric field on the right side times pi r squared, because that's the area of the right side, times cosine of theta on the right side, plus, and then we have the third face, which is the cylindrical curved face. So I'll call that E sub m for the electric field in the middle. The area of this curved cylindrical tube region is 2 pi r L. Oops, 2 pi r L, because you have a circle's perimeter and you're stretching that over a length L, times cosine of theta m. Okay? So that would be the flux through a cylindrical surface. Let's suppose that this is a horrible sphere, but let's just suppose it's a sphere of radius r. Okay. You can think about a sphere as a single curved face. The area of it is the surface area of the sphere. Okay, so the flux through the surface of a sphere is going to be it's going to be E times 4 pi r squared, because that is the surface area of a sphere, times cosine of theta, where theta is the angle between the normal to the sphere, which would point outward, and the electric field. Okay? So, one thing I want to point out is that when a surface is closed, we can define the area vector uniquely. So for closed surfaces, the area vector points outward. So I said that if you have an open surface, such as this one, you have two options for your area vector, but if it's a closed surface, you can uniquely define the area vector as pointing outward. Okay? And so what that means is that, let's suppose you have a surface, like here I have a spherical surface, and maybe the electric field is pointed out, away from the center of the sphere. Okay? And in this case, the flux through that surface is going to be positive. Okay? Because the area vector points out and the electric field points out. And so therefore, the electric field points out and the area points out, so the angle is less than 90 degrees, which means the cosine theta term is positive. Okay? If you have a situation where the electric field points inward, maybe you have an electric field that goes in like this through this surface, in that case, the flux through that surface is going to be less than 0. Okay? So, let's go ahead and do an example. All right. Let's suppose that we have a cylinder. All right. And let's suppose that the electric field points in like this. Let's say this is a 10 Newton per Coulomb electric field right here. And it makes an angle right there of 60 degrees. Okay? And then along this edge of the cylinder, we have an electric field that points up and down. Okay? And so let's suppose that that electric field has a size of 300 newtons per coulomb. Okay? And then along the middle section of the cylinder is an electric field that points radially outward. So it points away from the axis of the cylinder. Like that. Okay? Directly away from the axis of the cylinder. Okay? And so that means that it's always at a 90-degree angle. It's always at a 90-degree angle to the surface. And the strength of that electric field is 5 newtons per coulomb. And let's suppose that the length of this cylinder is 4 meters, and the radius of this cylinder is 1 meter. Okay? So, how are we going to do this? We want to get the flux through this. We want to get the flux through this surface, E dot dA, and it's going to be made up of 3 parts. There's the left cap, there's the right cap, and then there's the center region. Okay? So this is going to be, and one thing I want to point out is that the flux through the middle region is positive, okay? Because the electric field is going out through the surface. And then for the left cap, the flux is going to be negative because this electric field is going in through the left end cap. And the flux through the right end cap is going to be 0 because because the electric field is going up and down, and the area vector points out, so there's a 90-degree angle between the area vector and the electric field. So really, I have the electric field on the left side dot the left area plus the electric field on the right side, or on the middle side, dot the middle area. Okay? So the left electric field, it's going inward, so I'm going to make the flux negative. The size of the electric field is 10. The size of the area is pi times 1 squared. And then the angle between the normal and the electric field is 60 degrees. So I have cosine of 60 degrees. So that is the flux through the left side. Through the middle side, I have a positive flux. And so the size of the electric field is 5. The area is 2 pi r, which is 1, times L, the length is 4 meters, times cosine of the angle between the area and the electric field. Now remember, the area vector points perpendicular to the surface, and the electric field also points perpendicular to the surface, as I said, by definition, by what I said, okay, in this particular case. So that means the angle is 0 degrees. All right. And so the cosine of 0 is just 1. So let me work that out. And I get a total flux of plus pretty much 110 Newton meters squared per coulomb. Okay. Let me just do one more really brief example. What if you had a sphere, and what if the electric field everywhere points outward, away from the center of the sphere? In such a way that the electric field is always perpendicular to the surface. like that. Okay? In that case, the flux through the surface is going to be just E times 4 pi r squared. Okay? Because the cosine term is going to be 1 because it's perpendicular at all points. So that is an important one to know. All right. So let's talk a little bit about what does this mean? What is flux intuitively? Basically, flux, it counts the number of field lines passing through a surface. Okay? So that is what flux is doing intuitively. So, for example, what if I have a positive charge here? And the positive charge has its electric field lines that go radially outward. Okay? What if my surface was something like this? Like, what if this was my surface right here? So that, and this surface is like edge on. You can see that 3 electric field lines pass through that surface. I'll try and draw it 3D. So 3 electric field lines are puncturing that surface. So I would say that the integral of E dot dA is 3. Okay. If you had more charge, like maybe you put 2 charges, so that's going to have twice as many lines. So we're going to have twice as many lines puncturing the surface. You get what I'm saying? And that's going to change the value of the flux. Okay? So intuitively, it's counting the number of field lines passing through a surface. So now we're going to get to the major statement of today, which is called Gauss's law. I froze for a second there. So Gauss's law, and I'm going to explain Gauss's law intuitively in the next lesson, but let me just state it. What it says is that if you have a surface and you calculate the flux of the electric field through that surface, it is going to be equal to the charge enclosed by that surface divided by epsilon naught. Now, epsilon naught is a constant of nature. It's called the permittivity of free space. Or you can just call it epsilon naught. That's what most people call it. Its value is 8.9 times 10 to the minus 12 farads per meter. So it has weird units. Don't worry about it for right now. Okay, so that is the value of epsilon naught. Okay, so let's see how would that work. What if I had some really weird surface? So I have like some weird surface. Okay, so it's some weird closed surface like that, okay? And what if inside it I have a plus q charge and I have a minus 5q charge and I have a plus 2q charge, okay? And then maybe right here I have a, I don't know, a plus 100q charge. This charge is not enclosed by the surface, so it's not going to affect the value of the flux through that surface, okay? So the total amount of charge is plus q, plus 2q is 3q, minus 5q, so that's minus 2q. So I would say that the value in this particular case is minus 2q over epsilon naught for the value of the electric flux through that surface. So what Gauss's law does is it relates the flux of the electric field through a surface to the charge enclosed by that surface, okay? So we will talk more about this in Thursday's lesson.